During the first time our body sees a microorganism, if we get sick or if we have a vaccine, then we'll make a primary response. So it turns out that there are different antibodies in the body. IgM is a very big antibody, IgG is a very small antibody. So what happens during an infection, this is x-axis showing weeks, y-axis showing the titer, which is the number of antibodies. So during a primary infection, the first antibody produced is actually IgM, the bigger one, and then second we see a peak of IgG. And during a primary response by a vaccine or vaccine injection or a sickness, the IgM and IgG levels are pretty similar. The IgG gets a little bit higher around the second week, but then after the first week, we see this bump in IgM. So IgM comes first, and then later IgG. But the levels are pretty comparable, a little bit higher for IgG. However, if you get exposed to that microorganism again, or you get a booster dose, a second dose of the vaccine, what happens is you get way higher IgG levels than IgM. Very, very significant difference, where the IgG titer, number of IgG antibodies, will far greatly outnumber the number of IgM antibodies. So the secondary response to a pathogen is much stronger, and it's IgG primarily instead of the initial response having more IgM initially and then a little bit higher levels of IgG later. So the basis of immunity, like when you get the flu shot, the first time you get a flu shot, you get initial IgM and then more IgG. But then when you take, if you actually were exposed to the flu, right, but you've been vaccinated, your IgG is going to jump up. Look how high it is, right? So like it's going to jump up really quickly and prevent you from getting sick. So this is really important and the basis for immunity. And so the secondary response is characterized by a much, much higher IgG to IgM. The IgG to IgM ratio is higher, whereas in the primary response, there's not so much of a difference between the IgM and IgG, but IgM would peak first in a primary infection or vaccination. So now I need to introduce the different forms of acquired immunity. So what I've been focusing on today were active immunity. So we have natural active immunity, and this is natural active is from where we get antibodies or activated lymphocytes that are produced as a result of an infection. That's acquired immunity. Acquired active natural, okay? We also can have acquired artificial active immunity. So artificial active immunity results from antibodies being produced as a result of immunization with the vaccine. For the flu shot, they just inject flu peptides under our skin. We're not getting sick because it's just a peptide, it's not the whole flu virus. There's also natural passive immunity, and this is where antibodies are passed to a fetus through the placenta or in the colostrum, which is the first breast milk that a baby has after birth. So that is natural passive immunity. And finally, I need to introduce artificial passive immunity, and this is where antibodies have been produced in another animal, or animal, for example, and then they are, or they're produced in a test tube, and then they're given to an animal or a person. So, for example, if you've been bitten by a rattlesnake, you can get a rattlesnake antivenom or antibodies in the hospital that'll prevent the poison from affecting your nervous system. If you've been exposed to the botulism toxin, there's also antibodies that you can get that will then help protect your nerves again from the botulism toxin. So how can toxins be protected against? So here's a susceptible cell, here's a toxin. The toxin can obviously bind and get to the cell and damage it. Now, if that toxin is bound by an antibody, the antibody will protect the cell, and the toxin will bind the antibody instead of the cell, and it will protect the cells from getting destroyed by the toxin. A similar thing happens with viruses. So here's a virus, and then there's antibodies to the virus. If the virus is coated with antibody, the virus will no longer be able to infect the cell. And last, I'd like to show you some more about opsonization and how both antibodies and complement are very important opsonins. And these really determine the efficiency of phagocytosis. So if we look at the first cell, here's a macrophage and a bacterium. The bacterium is not coated with any opsonin. So the macrophage is going to detect either the LPS or the peptidoglycan, and it'll phagocytose it, and there's no opsonin, right? So it'll happen at a low level of phagocytosis and binding. However, if there's an antibody bound to the bacterium, the macrophage will grab onto the Fc portion of the antibody. The Fab portion is going to bind it to the microorganism. We see that phagocytosis is going to be much more efficient because of the antibody binding to the microorganism. Even better at stimulating the phagocytosis is the complement C3b. And this is like a spoon, and basically the macrophage will even have better enhanced phagocytosis compared to the antibody when complement is bound to a bacterium. And then the best, even better than that, is when we have both antibody and complement bound to the microorganism, then we see the greatest enhancement of phagocytosis. And I just want to remind you that the complement is part of the innate immune system, and the antibody is produced by the adaptive immune system. It's when the adaptive and innate immune systems work together when we get optimum immunity. So thank you for your attention, and please go over this material, and I recommend it's really important to draw it out, especially on those one-page of notes. It will be really important to draw out all the immunological processes and to really think about how each process could work against a gram-negative bacterium, a gram-positive bacterium, or a virus. If you can apply it in that nature, it'll really help you to have a better understanding of these processes. So thank you for your attention and have a great day. Take care.